All right, looking today at our first topic in Unit 1, moles and molar mass. So atomic structure and properties is our Unit 1, and we're going to look at the first topic today. The enduring understanding the mole allows different units to be compared. So through a couple of the topics in Unit 1, we'll be looking at this particular enduring understanding. For the learning targets, by the end of the PowerPoint, you should be able to calculate quantities of a substance or its relative number of particles using dimensional analysis and the mole concept. So the dimensional analysis, the T-charts, being able to convert between quantities like molar mass and particles and liters and things like that using the mole map. That's what you should be able to do for that point. And explain the quantitative connection between the mass of a substance and the number of particles that the substance contains. That's once again going back to the mass, that molar mass related to the mole, which helps relate it to the number of particles, and we'll be able to utilize that in this PowerPoint and in these problems. So looking at a basic concept setup here for our warm-up. Since we haven't looked at calculations in a while, I thought I'd start with something pretty basic. Student has 17 gram sample of iron 3 chloride. Show the setup including the units of the calculation to determine the number of moles of iron 3 chloride in the sample. Express the answer with the correct number of significant figures in units. Okay, so we're going to be showing our work here at all times. Now, if we're looking at our problem here, we have 17 gram sample of iron 3 chloride, and we're looking for the number of moles. So what we need to think here is we've got grams, we've got moles. What is the conversion that needs to take place? We need to be looking at molar mass. So let's review our conversion factors using the mole map here real quick. Make sure we understand where we're getting our molar mass from. So looking at the different mole maps, I gave you one over here with just the arrows and the conversion factors, like particles is Avogadro's number, 6.02 times 10 to the 23rd. If you're going between moles and grams, you're going to do it by molar mass, which involves using the periodic table here. And the last one is 22.4 liters. Now that is a conversion factor for any gas at standard temperature pressure. Standard temperature pressure, of course, is 0 degrees Celsius, 273 K. For the temperature, standard pressure is 1 atmosphere, also 760 millimeters of mercury, or we have 101.3 kPa. And remember that standard pressure is the atmospheric pressure at sea level. So those conversions there, we can use any of them in our problems when we're going, because they all equal 1 mole. They all equal 1 mole. And Avogadro's number here, remember particles isn't going to be next to the compound or the element. What you'll see is either atoms, ions, formula units, or molecules. And what you need to make sure that you understand about these things, they're signifying different types of substances. And these different types of substances, let's take a look here. Atoms, of course, is representative of just elements off the periodic table. Ions, of course, are going to be charged elements off the periodic table where they've lost electrons, like lithium +1 or F-, or even the polyatomics like nitrate, NO3-. Anything off the periodic table, iron 3, that's in the iron 3 chloride compound. So you can see anything that has a charge is going to be considered an ion. Now, formula units are for ionic compounds. So that's going to be metal plus non-metal compounds, or ones that have polyatomic ions in them. And then this last one here, molecules, is for something that has a covalent bond. Covalent bond You can have covalent compounds where it's two different elements like carbon dioxide, water. These ones have two different elements, so they're considered covalent compounds. Or you could see the diatomic molecules, the diatomic elements in here, like O2, F2, Cl2, Cl2, excuse me. Those are all considered molecules because they have covalent bonds in them. So that's a way of defining the different types of particles, is by these particular names that you'll see in the problem next to them. If you see any of those, atoms, ions, formula units, molecules, you're going to be using Avogadro's number. Now, of course, you're going to need a periodic table. So there's a link here that you can click on to pull up the College Board periodic table. Notice that they do not have the names on here. It's just the symbols. So you have to really start using this one a lot and familiarize yourself with it and get those symbols kind of memorized. Not really memorized, but easily where you can locate them fast. Once again, time is always an issue in AP because you're going to have timed only a certain amount of time for the AP exam. So make sure you're very familiar with where to find things on the periodic table. But you definitely want to have this up, especially when you're doing math problems where you have to look up molar masses. And for the molar masses, I want everybody to always round to 2 decimal places. Looks like on here, they're all rounded to 2 decimal places for the most part. Yeah, it looks like they are. So we're going to always round ours to 2 decimal places when we're using molar masses off the periodic table. So even if you're not using the College Board periodic table and it's not handy, make sure you round all of your molar masses to 2 decimal places, hundredths, okay? Now let's go over this one again. So we have 17 grams of iron 3 chloride. So we're going to create a T-chart, start there, put our given information in the upper left corner. That's what we always do. Oops, Cl3. There we go, upper left corner. Now, got to convert, so I need to be able to get rid of my grams. So I'm going to take those grams and I'm going to diagonal them down. Grams of FeCl3. That means I can go to moles using my mole map. And everything on the mole map equals 1 mole. Now all I have to do is go ahead and add up the molar mass of iron 3 chloride. So if I look up iron on my periodic table, that's 55.85. And the chlorines, they're 35.45. But there's 3 of them, so I need to multiply that by 3. Then I need to add it all up, and then I can get my molar mass. So if you go ahead and add all that up, that should be 162.2 grams. Now I'm ready to cancel. So the grams of the iron 3 chloride cancel with the grams of the iron 3 chloride. And all I have to do is multiply the top 17 times 1 divided by the 162.2. And I should get my answer. Now another thing we need to consider before we, you can do the calculator answer, write it down, but then you need to look at rounding. So if we're looking at this particular problem over here, the significant figures, we want to look at those. We want to see that because of the decimal point, we start from the left, start counting. So the first non-zero digit is a 1. Now everything after that counts. So this particular measurement has 3 significant figures. That means my answer should also have 3 significant figures. So when you go ahead and multiply and divide, so I end up getting a calculator answer of 0.10480. So this is the calculator answer. If I'm looking to rounding, I go to keep the 1, keep the 0. The 4 is the one I'm going to round now. Round it up because this is a 5 or above next to it. So then the answer is 0.105 moles FeCl3. So don't forget your unit and your substance in your answer there, okay? And that would be correct if we're looking here at our T-chart set up here. 0.105 moles FeCl3. That's the basic. This is a one-stepper. Anything to moles is going to take 1 step. So let's go ahead and take a look at another example. this particular case, a student has 41.9 grams of dinitrogen monoxide. Show the setup calculation to determine the number of molecules. Now we're going to molecules. So we're going from grams over here to molecules. And I abbreviate molecules MLCS. But that means we have to make a pit stop at the mole first. So we're going to have to convert to moles. So this is the first step. Then we're going to have to convert to molecules. So it's going to take 2 steps to complete this problem. So we have 41.9 grams of N2O, dinitrogen monoxide. So that means grams of dinitrogen monoxide goes down here. That's going to equal 1 mole of dinitrogen monoxide. So we add up the molar mass. We have 14 times 2 plus the 16. We add all that up and we get our molar mass. So our molar mass happens to end up being 44.02. So we're going to put that in here, 44.02 grams. Now, once again, we're going to go all the way over here to molecules. So we need to add on another step to our T-chart. This time I'm going to take the moles and diagonal them down. So 1 mole N2O is going to equal molecules. Now, molecules is the buzzword for Avogadro's number. That's 6.02 times 10 to the 23rd. So that's what I'm going to do here. Put the molecules of N2O. Now I'm going to be ready to multiply and divide. Going 41.9 times 1 times 6.02 times 10 to the 23rd divided by the 44.02 times 1. So really it's 41.9 times 6.02 times 10 to the 23rd over 44.02. Now, also on your calculator, when you're using Avogadro's number, don't forget to use the E button. It's really like a double E button above, it's the comma above the 7 if you do the second. You want to use this notation. It's easier and it doesn't mess up the order of operations in the graphing calculator. So go ahead and calculate that. And we will look here for significant figures as well. 41.9. So that means there's 3 sig figs in our measurement to begin with. So we need to have 3 sig figs in our answer. So we end up having 5.730 something here. So if I'm rounding it to 3, 1, 2, 3, that's a 0, so I'm not going to round it up. So it ends up being 5.37 times 10 to the 23rd times 10 to the 23rd molecules N2O. Make sure you use the unit substance next to the answer when you're expressing your answer. And looks like we got that correct here. So same answer, molecules N2O. All right, so now we're going to do a little reviewing of some conversion steps that you can take that you might not be aware of or remember from last year. So if we're looking at propanoic acid here, this C2H5COOH organic molecule, how many hydrogen atoms are actually in this molecule? Well, there's 5 here and 1 here, so that would be a total of 6. Now, how can we set up conversions using hydrogen atoms in propanoic acid? Okay. Well, if you think about it, if there's 6 hydrogen atoms in 1 propanoic acid, you can relate it to 1 molecule of propanoic acid equals 6 hydrogen atoms. Now remember, propanoic acid, those are all covalent bonds. It's all non-metal, non-metal. So that's why we're going to call this the molecule. Now, why can we use the mole in the conversions? Well, we can translate this also to the mole concept because the mole is a counting unit. And since we're counting number of atoms in a certain, particular molecule, we can also label it as moles. So 1 mole of propanoic acid is going to be equivalent to 6 moles of hydrogen. So when we set up our T-charts, these are kind of different ways that you can set up your conversion factors. You can flip them too. You could put the molecule of propanoic acid on the top and the 6 hydrogen atoms on the bottom. Just like over here, you could flip and put the 1 mole of the propanoic acid on the bottom and the 6 moles of hydrogen on the top. This is something that you can use in your when you're converting if you have to go to a particular atom within a compound, and even go further down the line. All right, another concept we need to review is the idea of this formula. And maybe you remember from back in the day that we did PV equals nRT, which is the ideal gas law, and they introduced the new variable N to you. You know, P pressure, V volume, T temperature, R is the constant. Well, N also represents this particular variable in the equations. The N is going to represent moles. Now, I'm sure you probably figured out too that the lowercase m here, that's molar mass. Mass, that's just mass, because we always think of the lowercase m as mass. And the big M they're going to be using is molar mass, grams per mole. And this is how it appears on the formula sheet. So check out that formula sheet. Now, I do find the big M a little confusing. I like to use big M for molar mass, because big M to me is really moles per liter, which happens to be molarity, but they use it both ways on their formula sheet. So no, you can check the formula sheet for the molar mass. And molar mass is really a measure of grams per mole. So here, and that's how we end up being able to cancel to get our units in place. Now, something you can do with this particular equation is rearrange the variables. And if you rearrange the variables, erase that real quick. Rearrange the variables, you can use it to and manipulate it so that you can find molar mass. And they like to do this because they want to see that you can rearrange the variables and understand that molar mass is equivalent to the grams over the moles here, and using that equation. So that's why I put this in here. Reviewing, you may have not thought about it this way in terms of that, but it is, a derived unit, grams per mole, molar mass, just like density is like grams per milliliter, something like that. All right, so let's take a look at an example problem here where we're going to use some of these concepts. So how many hydrogen atoms are in a 2.6 gram sample? Gram sample of, I'm going to erase that real quick. There we go. Of ethanol, another nice organic compound with that OH group on the end, that hydroxyl group. So we're going to set up this calculation, label the conversions, and express our answers with the correct number of sig figs and units like before. Starting over here, my given information goes in the upper left corner, and we're dealing with ethanol here. Okay, so I'm starting there. Now, I need to get to hydrogen atoms. That's going to take a little bit to get there, because first of all, I have to do grams to moles, because I have to make a pit stop at the mole. That's on my mole map. Then I can go to molecules, because I have, covalent compound here. And then once I get to molecules is when I can now break it down into the atoms. So this is going to take 3 steps to get to our final conversion here. So we do grams of ethanol here on the bottom, diagonal that down to get rid of it so it cancels. That's going to equal 1 mole C2H5OH. And we add this up, I believe it's 46.08 grams per mole. 2 carbons, 6 hydrogens, 1 oxygen on the periodic table. Add that up, you get your molar mass. Now that we're here, now we're going to take our moles now and diagonal them down. So moles of ethanol is going to give you molecules of ethanol. So 1 mole, of course, equals Avogadro's number, 6.02 times 10 to the 23rd molecules of ethanol. And we're not done yet, though, because we don't want molecules of ethanol. We actually want the hydrogen atoms in ethanol. So we're going to take this molecule now and diagonal that down. So 1 molecule of ethanol is equivalent to 6 hydrogen atoms. Now that we have it all set up, we can work on multiplying, dividing, and canceling. All right, so now we're going to cancel grams with grams of ethanol, the moles of ethanol with the moles of ethanol, the molecules of ethanol with the molecules of ethanol. And now we're left with atoms, which is what we wanted anyways. Looking at significant figures over here, we have 1, 2, 3, 4. So that means our answer will need to have 4. So we multiply the 102.6 times the 6.02 times 10 to the 23rd times the 6 on the top. Hit enter and then divide by your 46.08. You should end up with 8.0423 4 something. Okay, so let's round this number. So let's round this number to 4 significant figures. Keep the 8, keep the 0, keep the 4. This is the 2. This is what we look for rounding now. The 3 next to it means we're going to leave it a 2. We're not going to round it up. So it's going to be 8.042 times 10 to the, don't forget the particle number in the calculator, times 10 to the 24th atoms of hydrogen. And let's check here with our answer. We're correct here. Very good. Now we're looking at exercise 3, a different type of problem. This is going to involve looking at other things that with regards to moles and molar mass and conversions. And let's go ahead and read through the scenario, underline important information. That's the best strategy to start with. Student has a 20-gram sample of each of the following compounds. We have barium iodide, magnesium chloride, and strontium bromide. List the samples in order of increasing number of moles. So increasing number of moles in the sample without making calculations. Explain your answer. Okay, so we don't really get to show it by calculating. You're supposed to show it by concept here. So what we want to start with here is determining the relationship between the numbers. So we have grams, we have moles, and how are these two related? Well, if you go back to the equation, N equals mass over molar mass. Okay, so the moles equal grams per over grams per mole, like that. Okay, so we'll be referencing this equation to explain our answer, and that's kind of what they wanted you to do here. Now, of course, before we can continue, we know that the grams, or the top number, is going to be 20 for each of them. But we want to look at the relationship between the other two numbers, the moles and the molar mass. If I look at the periodic table for my compounds here, I can get a relative idea of the molar mass. So that's where I need to look now and compare them on the periodic table without actually calculating their molar masses. And if you look here, we have the barium and the iodine, these two together. Okay, so that's our first compound, barium iodide. We have our strontium bromide, that's one of our compounds too. And last but not least, we have our magnesium chloride. And as you can see, the way the problem is worded is so that you see elements in the compounds are from the same groups. So this is the alkaline earth metal group 2, the group 2 metals, alkaline earth metals. Group 17 is our halogens. So they gave us kind of an easy way to compare the trends between the different molecules. So who has the greatest molar mass out of these three? Well, barium's 137, iodine's 126. This one's definitely going to have the largest molar mass, the greatest molar mass. And also that's true about magnesium chloride, is that because the number's the smallest, the 24.3 and the 35.45, this is going to have the smallest amount for its molar mass, or the least amount for its molar mass. Strontium bromide would be in the middle. Now that we know those particular, references, we can reference the relationship in our answer. So looking here again, referencing the molar mass equation, N equals M over M, we can decide here that as the bottom number, this denominator gets larger, that means the mole number is going to decrease or go down. So if we increase the molar mass here, the mole number should go down. So in your explanation, you should reference the equation, okay, looking at the mass over molar mass equals the mole equation. Determine the sizes of the molar mass, which we did. We said barium iodide is the greatest and magnesium chloride has the least. So we'd say that in our answer. So according to the equation, if we put 20 grams on top for each one, the larger the molar mass, the smaller the amount of moles in the substance. So that would be this is the explanation, the key explanation here. Establishing that relationship between the moles and the molar mass. The greater the molar mass, the less amount of moles if the gram sample is the same for each compound. In this case it is, it's 20 grams. And we would list out our increasing number of moles. So barium iodide would have the least number of moles, strontium bromide would be in the middle, and magnesium chloride would be the compound with the greatest number of moles. Last but not least, this is an interesting question, and it looks very confusing because they're talking about some random compound, antibiotic penicillin G. Like, what is that? But what you're going to see here is this problem isn't as tough as it seems. You just have to use what they give you and set it up so that you understand where you're doing your calculation. So let's read through very carefully and take a look at what they give us. It says 1 molecule of antibiotic penicillin G has a mass of 5.554 times 10 to the minus 22nd grams. What is the molar mass of the penicillin G? Set up the calculation, label conversions, and so forth. Well, let's look at what we got. We got mass. We want to find molar mass, okay? So how are they related? Well, if we're using our equation here, rearranging our variables, molar mass, of course, is then going to be mass over moles. Now, they didn't really give us moles, but we can see what we can do with moles. They did give us molecule, 1 molecule though, and we know molecules can be translated to moles or converted to moles using our mole map. So let's set up what we have. We have 5.554 times 10 to the minus 22nd grams. I'm just going to put PG for penicillin G since I don't know its formula off the top of my head. And you're like, why don't we know the formula? Well, we don't need to know the formula. You'll see it's going to work out just beautifully here. But it's this 5.554 times 10 to the minus 22nd grams. That's per molecule. So I would put 1 molecule on the bottom here. So this is the amount of grams per molecule. Now, if you think about it, if we convert this, because we want to have the grams over the moles. Well, we already have grams on top. We want to keep that there. So really what we need to get rid of is the molecule. And the molecule's on the bottom this time. So this time we need to diagonal it up. So molecules need to go up here. And we know that molecules, will equal 1 mole. That puts us in a nice position to have mole on the bottom to get our molar mass here, which is what we want. So how many molecules in 1 mole? That's Avogadro's number, 6.02 times 10 to the 23rd. Molecules, PG, in 1 mole of PG. So this nicely cancels for us. If you see here, the molecule is going to cancel with the molecules here. And what are we left with? Grams per mole, which is what we want anyways. So when you multiply these out, you're going to look for sig figs too. We want 1, 2, 3, 4 significant figures in our answer. And make sure you use that E button to do your exponents on your calculator here. It makes it so much easier. And let's see what we would get here. The 334.4 grams per mole. And then, yes, we should have probably put PG over here, our substance. So 4 significant figures, since we have 4 up here in our beginning problem. So round that up. that is how you would approach a problem like that, where you can set up the dimensions and be able to cancel it. And it does look complicated at first, but take it at face value and just set up what you have. And you'll notice that most of the time it does cancel nicely.